I have noticed that the way we usually teach statistics relies a lot on memorizing formulas and applying them in a repetitive, almost programmed way. As a result, even those students who can successfully solve the problems on their final exam rarely truly understand what they are doing. I think, however, the main objective in learning statistics is to build an intuition about its main principles. After all, the formulas are just mathematical consequences of these principles, and without understanding the latter, the math itself is pretty useless on solving real-world problems. This video is my attempt to introduce to you the essence of statistical inference in a formula-free way. Let us simulate a situation. You are tasked to estimate an average person's height of a large population, say France. Naturally, you cannot go and measure the height of every single person to get the answer. So what you do is randomly select a sample from the entire population, a specific group that you will collect data from. You then compute the average height of the sample and get some number. The question now is this value exactly equal to the mean height of the entire population? The answer is, in general, no. After all, we didn't measure the entire population, only a random sample from it. To highlight this fact even more, we may ask another question. If we redo the experiment and select another random population sample, would its average height be the same as the first sample's? And again, the answer is no, it probably wouldn't. And if we continue selecting random samples and computing their average height, we would get a slightly different value each time. Now, what if I tell you that understanding this property of random samples is, in my opinion, the key element for intuitively understanding statistical inference? You see, what we have just agreed on is that the average height estimated from a random sample is a random variable itself, which is a fancy way to say that it may take different values each time we do a measurement. But what are the values this random variable can take? Are they limited by some range, or it can be any value at all? Are all the values equally probable, or are some of them more likely than others? We call the probabilities of occurrence of different possible outcomes of an experiment a probability distribution. In our case, the experiment is taking a random population sample and computing its average height. We can try to estimate its probability distribution empirically. For that, let's continue simulating random samples from our population and gather its average heights. After a while, a distribution pattern starts to emerge. The point density seems to be non-uniform and is high in the middle. To be more precise, let us quantify this distribution. For this, we split the number line into even intervals, or bins, and count how many points lie in each of them. The resulting graph is called a histogram. Let's continue our simulation. We can see that the histogram eventually forms a particular bell-shaped curve. We shall call it a probability density function. And its name speaks for itself. It is a kind of continuous representation of the point density on the number line. And what it means is that the random variable is more likely to take values from the regions with a high probability density. You may also notice that the histogram and corresponding density function are centered at some value, 169 in this case. And as a matter of fact, 169 is the average height of the entire population that I have simulated. Let us summarize what we have discovered so far. We have empirically showed that first, the average height estimated from a random population sample is a random variable itself. Second, the density function of this variable has a particular bell-like shape. It means that this variable has a higher probability to take values close to the center of the curve and less likely to be far from it, yet it is still possible. And 3. This density function is centered on the average height of the whole population, the value that we want to estimate in the first place. A legitimate question to have, however, is of what practical use are all these observations? After all, we cannot perform hundreds of different population samplings to estimate the histogram of their average height and thus estimate the average of the whole population. All we have in real life is a single population sample and thus a single value of the average height estimated from it, and it corresponds to a single point on our number line. Well, here is where the mathematical theory of probability and statistics play its role, and it says that the shape of the density function can be analytically defined. In other words, we don't need to empirically perform multiple samples to reconstruct the histogram as we did in this simulation. Statistics tell us precisely what is the shape of the density function associated with the mean value of a population sample. But what it doesn't tell us, of course, is where the center of this density function is. In fact, it can be centered basically at any positive value. But not all the center values are equally likely. Indeed, one would expect the observation value that we computed from the sample to be more likely generated by this distribution rather than by this one. And given the exact shape of the density function, we can measure this fact quantitatively. Let's do the following trick. We first define the interval around the distribution mean value such that the probability of the corresponding random variable taking value from this interval is equal to some arbitrary number, say 95. If you are not yet familiar with the concept of probability density function, you may think about a histogram where we select bins around the center containing 95% of all point samples. For lack of a better name, we will call it an interval under the curve. Note that the larger the probability we choose, the larger the corresponding interval. We now consider all possible mean values of the distribution and choose those which contain our sample inside the interval. What we have just done is we have constructed a confidence interval, a range of values for the population average height. It means that we estimate the real population average to be inside this interval with a confidence level of 99%. There is always a trade-off between the length of the confidence interval and the value of the confidence level. By decreasing the confidence level, we inevitably decrease the confidence interval. I will let you think why it is like this by yourself. The clue is to understand the link between the interval under the curve and the resulting confidence interval. In this particular case, the real population average height of the French population lies inside this interval, yet it is not guaranteed. The confidence level that we have chosen is 99%, which means that there is still a 1% chance that we select a random population, compute its average height, build the confidence interval, yet the average of the whole population is not in it. Moreover, if in this particular case we have chosen a slightly smaller confidence level, say 95%, we would get a smaller confidence interval and it would not contain the true population average, simply because of bad luck. And this is an important example to have in mind. Statistics doesn't do miracles. It quantifies the risks. So, let's summarize the main points once again. The average height, estimated from a random population sample, is a random variable itself. And to better understand that, try to ask yourself what would happen if you select another random population sample and compute its average height. From the theory, we know the general shape of its probability density function, but we do not know its mean value. If you are not yet comfortable with the notion of density function, replace it with histogram. We use this density function to define an interval around its center, corresponding to some arbitrarily chosen confidence level. The confidence level defines the probability that random value generated by the density function is located inside this interval. Finally, test all possible locations from the density function center and select those which include the value that we've got from the random population sample. The smallest and the largest value define the confidence interval. Let me say that, except for some details, this general framework is true not only for mean value, but for other parameter estimation from a random population sample, for hypothesis testing, etc. Moreover, all the formulas that are usually presented in the textbooks on this topic are just a mathematical representation of the principles that we have covered today. Although the devil is in details and all the math and formula are really important, I'll keep this video formula free. But if it gets enough interest, we may explore this topic in further detail in future videos.